Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will apply Bayes' theorem to the simple linear regression model. Let's begin. So, first, let me remind you what we have done thus far. So, in another video, we already talked about the likelihood of a single observation and of a sample of size n from the simple linear regression model, or to be more specific, the alternative simple linear regression model. And it looks like this, right? So this is the likelihood for a single observation. We know that if we want the likelihood for an entire sample, since we're assuming that the observations, that the errors are independent, then the observations are going to be independent, and then the likelihood for a sample of size n will be the product of terms that look like this. It will be the likelihood of the sample will be the product of the individual likelihoods. Okay? So we have something like this, right? And then we did a little bit of algebra, right? And we were able to express the likelihood of a sample, right, for alpha, x bar, and beta, the parameters of the alternative simple linear regression model form. So we were able to rewrite that likelihood as the product of two independent likelihoods. Remember, we did a little bit of algebra, a little bit, and then we were able to express that likelihood as the product of two independent likelihoods. One depended on beta, the other one on alpha x bar, right? The two parameters for that model that we're interested in. Now, we also said that note that the likelihood for beta is proportional to the kernel of a normal with mean SSXY divided by SSX and variance sigma squared divided by SSX. On the other hand, the likelihood for alpha x bar is proportional to normal with mean y bar and variance sigma squared divided by n, right? Okay, so we have a very important ingredient that we need to apply Bayes' theorem to this model, the simple linear regression model, right? The other ingredient that we're going to need is the prior, and then we know that Bayes' theorem, right, and the Bayesian approach could be summarized like this. Posterior distribution is proportional to prior times likelihood. Okay, so let's do the math here, the details, and then we are going to see that it was really important to be able to express the likelihood for alpha x bar and beta, right, as the product of two independent likelihoods, because that is going to allow us to consider two independent priors, and then the posterior will be the product of two independent posteriors. Okay, so here we go. Let's talk about the details. So likelihood. Let me write it like this in a generic form, right? Could be P or F, right, to refer to that function. So let me use that P notation in this case. So we could think about it as probability function that is conditional on the parameters of interest, right? So the probability of observing that sample given particular values for the parameter alpha x bar, that's what we call it, and beta, right? So that guy, what we said is we did a lot of algebra to show that this guy is proportional to the product of two independent likelihoods, right? We spent a good amount of time to show that, but it's going to be worthwhile in the end. You'll see. Okay, so now let's make an observation. Note that, right, this guy here, the likelihood for alpha x bar, right, is proportional to a normal with mean, and we can go back to our presentation here, but it's going to be proportional to a normal with mean y bar and variance sigma squared divided by n. Okay, so proportional to normal with mean y bar, variance sigma squared divided by n. On the other hand, the likelihood for beta is proportional to another normal, but this one with a different mean and different variance. The mean is going to be this guy, SSXY divided by SSX, and the variance sigma squared divided by SSX. Okay? So here we go, mean SSXY divided by SSX, and this guy here is going to be sigma squared divided by SSX. Okay, so prior. So before we talk about priors, given that we have normal likelihoods and they are independent, right? Thing is, given that we have normal likelihoods, it is just natural that the kind of priors that we would like to consider are either normal priors or flat priors, right? Because we know how to deal with those. Remember that we are assuming that sigma squared is known. So we have talked about that case before, right? So let me just in a very generic way here refer to the prior, right? Now we need a joint prior because we have two parameters, right? Alpha x bar and beta, those parameters for the alternative form of the least squares regression line, okay? And what we're going to be doing is, since these likelihoods, well, since the joint likelihood for alpha x bar and beta can be expressed as the product of two independent likelihoods, we're going to consider independent priors. That's going to make our lives easy. Okay. Okay. And well, then we know, right, as we said at the beginning of today's video, that we know that the posterior, in plain English, we could just say that the posterior is proportional to prior times likelihood. So if we do that, right, if we use, using our generic notation here, now what we're going to have is that the posterior distribution is going to be, right, prior, well, we have that prior, right? That joint prior is going to be the product of those individual priors, right, or independent priors. And then we have these likelihoods. So clearly, right, once we do the math, right, what we're going to have is the product of the marginal posteriors, right, because then it would be this times this, right, prior for alpha times the likelihood for alpha, and then we would have times this. Make sense? So we have this, and then in the end what we have is that the joint posterior is just the product of the marginal posteriors. We could rewrite that like this. That would be the posterior right times the other posterior, the posterior for beta, right? So that's why it was so important first to introduce the alternative form of the least squares regression line, right? And then to do all the math with it for that likelihood, for that expression of the alternative form of the least squares regression line, because then we were able to re-express the likelihood as the product of two independent likelihoods, and then that allows us to have this kind of prior, and then the joint prior could be written as, we could consider a product of two independent priors, and then we are going to have two independent posteriors, right? Let me just say something more. Remember that A, uppercase A, right, the least squares estimate for alpha x bar was y bar. Here you are. Remember that the least squares estimate for beta, uppercase B, was this, right? So here you are. Okay, that would be, those guys are the means for these likelihoods, right? Okay, so now let's talk about the posterior, right? What we said is, well, since the likelihoods are proportional to normals, we could consider either flat priors or normal priors. So let's find the parameters for the posterior distributions, right? We know that if we have a normal likelihood and we consider either a flat prior or a normal prior, the posterior will be normal as well, okay? And to find the parameters of that posterior, what we use is our updating rules. So let's apply our updating rules for beta and alpha to obtain the parameters of our posterior distribution. Okay, so let me just say that parameters for let me say marginal posteriors, right? We are going to have one for beta and one for alpha. So let me start with the one for beta. So for beta, we have a normal likelihood, and we said we're going to consider either flat prior or normal prior. Let me consider the normal prior, and then you can do the flat prior on your own easily, right? Okay, so remember that the idea is this: when we talked about those, we introduced the concept of precision, right? So what we said is, okay, the precision is the reciprocal of the variance, right? So the posterior variance for beta, and let me call it beta star here, meaning the posterior precision for beta, okay, is going to be prior precision, right? So we are going to have a prior precision for that parameter beta, plus the sample precision. So now let me go back to what we had before. From our likelihood, that will be the variance for beta from the sample. So, and we know that the sample precision will be the reciprocal of this. So it would be SSX divided by sigma squared in this case. Okay, so here we go. So SSX divided by sigma squared. Okay, done. Now what we need is the posterior mean. Let me call it M of beta star. Okay, and we know that to find the posterior mean, if you have a normal likelihood and you have a normal prior, what you do is you take the prior precision, you divide it by the posterior precision, and then you multiply by the prior precision, plus, right? Now instead of having this, right, instead of having the prior precision in the numerator, you will have the sample precision and we need the, before it was the sample mean. In this case, what we need is the mean from the sample, and the mean for the sample is this guy. Okay. Another way of expressing the formula for the posterior mean for beta will be this. Remember that this guy, as we pointed out, SSXY divided by SSX, is the least squares estimator for beta, what we called uppercase B. Okay, so you'll see that expression like that in your textbook, for instance, if I remember correctly. Okay, so now we can do something really similar for alpha. Okay, so let's do it, and then with that we're going to conclude that well, this video, right? Okay, so let me copy paste this, and we're going to make changes accordingly. So now what we want is the posterior precision of alpha. So what we have is prior precision of alpha, and then plus sample precision. Then we refer to the previous slide, well, not the previous slide, but the other document that we had here, right? And the precision in this case for alpha x bar, right, is going to be sigma squared divided by n. So the sample precision is going to be n divided by sigma squared. Okay, so n divided by sigma squared. Okay, now let's find the posterior mean for alpha star. Well, for alpha, right? M star. So we know that what we need is the prior precision divided by the posterior precision then prior mean for alpha, and then instead of having the prior precision, we're going to have the sample precision times, and before it was y bar when we were talking about the mean mu, but let's see what it is in this case. In this case, guess what? It's going to match with that, because the least squares estimator for alpha x bar, right, for the intercept of the alternative form of the least squares regression line happens to be y bar. Okay, so it's the same in this case. So that's it, right? So the posterior for these guys, for alpha, x bar, and beta, is going to be just the product of two normals, right? And now we know that we could find those, well, the parameters for those normals, for those posteriors, just using the old updating rules. Okay? Just like we did before. And just as a final comment, remember that if you're using a flat prior, right, variance is infinite and then the precision is 0, right? And then just make changes accordingly, and then you'll get the parameters for your posteriors. Okay? So let's summarize what we just did here in this video. So we wanted to apply Bayes' theorem for the simple linear regression model, right? So we know that to do that we need our two main ingredients, the likelihood and the prior, right? So in this case what was key was that our likelihood for these two parameters of interest, right? Well, we did the math before in another video, so we could re-express that likelihood as the product of two independent likelihoods, one in terms of alpha, one in terms of beta. It turns out that they are proportional to normal PDFs, right? Probability densities, right? And then we know how to deal with normal likelihoods. We could use normal priors or flat priors, right? And then we know that to update the parameters of our priors, we need to use our updating rules, right? And then the joint posterior is going to be just the product of those two marginal posteriors, those two posterior normal distributions. Make sense? Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.